Hi everyone! In this video we are going to talk about nucleophiles versus bases a little bit more. So first I wanted to go over this summary table in your textbook. I really like this table because it really simplifies everything we've been talking about. So in this table, the rows are correlated with the type of carbon that's bonded to the leaving group. So for instance, if you have a primary carbon, then that's going to favor E2 or SN2. Because remember, if we form a carbocation, a primary carbocation is really unstable. So a primary carbon would prefer to go through a second order reaction, where the base or the nucleophile attacks first. So primary carbons favor E2 or SN2. Secondary carbons also favor E2 and SN2, typically. And then tertiary carbons favor E2, SN1, or E1. So what's kind of interesting is you can see that E1 reactions are very specific, like they need very specific conditions in order to occur. Now up at the top, the columns are correlated with what type of base or nucleophile you have. So for instance, if you have a strong base that is also a weak nucleophile, that will favor E2. Now, if you have a strong base that's also a strong nucleophile, you could have a mixture of E2 and SN2 products, unless you have a tertiary carbon attached to the leaving group. And then that favors E2. And then you can keep going. So if you have a weak base that's a strong nucleophile, that will favor substitution reactions. And that just depends then on what type of carbon you have. Do you have primary or secondary? That will favor SN2. But if you have a tertiary carbon, that favors SN1. And then if you have a weak base that's also a weak nucleophile, that will only give us SN1 or E1 products. Okay, so what we want to focus on today is figuring out how can you even have a strong base that's a weak nucleophile? How does that work? Or how can you have a strong nucleophile that's a weak base? What does that look like? So let's just kind of go through some of those different options. All right, so let's look at bases that are not nucleophiles. So remember in the last lecture, we said that nucleophile size matters. So if you have something that's really bulky, that won't be a good nucleophile. However, size doesn't matter for bases. So option 1, you could use something that's really bulky, and then it will act as a base, and it won't act as a nucleophile. So one option is something called tert butoxide. And we actually saw this in the last lecture. And then typically there's a potassium ion that balances the charge on this base. So we can abbreviate this as KO and then lowercase t Bu. KOTBU. So potassium tert butoxide. So again, if you have something that's really bulky but has a negative charge, that's going to act as a base, but it's not going to act as a nucleophile. So that tert butoxide will take a proton, but it won't do nucleophilic attack. So then that would favor an elimination reaction. Okay, option 2, we could use a special base. So one of these quote-unquote special bases is called 1,5-diaza bicyclo 430 non-5-ene. So it's a really long name, but I swear there's an abbreviation for it. So this special base looks like the following. Let's see. I'll do my best to draw it here. Oh, I missed a nitrogen. There's a nitrogen at the bottom of the 6-membered ring. And again, this is called 1,5-diaza bicyclo 4.3.0 non-5-ene. But we abbreviate this DBN. So we just capitalize DBN. So if you want to use this base in a reaction, you don't have to draw the structure or memorize the full name. You could just write DBN and chemists will know what you mean. So you can just use that abbreviated form. Now, when this reacts with a hydrogen, or when it takes a hydrogen, so we'll just write H plus here above the arrow, the nitrogen on the bottom of the ring will take the hydrogen, and then we'll end up with the following. And this can actually go through a resonance structure. So electrons can move around. So the lone pair on the top nitrogen can move down. And then the pi electrons will move over to nitrogen on the bottom. And we'll end up with this configuration here. So these are, again, resonance structures. All right, and this is great because we do want a base that has a stable conjugate acid, right? Because that means it's a really strong base. And this is a really stable conjugate acid because of its resonance. All right, and then there's another base that's kind of similar to this one, but it's called DBU. And so that looks like, let's see if I can draw this, because there's a, let's see, 1, 2, 3, 4, 5, 6, 7-membered ring. And these are kind of hard to draw. I'm doing my best on this one. Oh boy, this looks pretty bad. Also, my pen is freaking out a little bit. All right, so sort of looks like this, and it's called DBU. So the full name is 1,8-diaza bicyclo 540 undec 7-ene. But all you have to know is it also has a stable conjugate acid, so it is a strong base. And it has similar resonance to the one up above. So you could use either DBN or DBU as strong bases that are not nucleophiles. and that will favor elimination reactions. Now, there is one more option. You could use an insoluble base. So what's really great is that bases don't have to be soluble in order to take a hydrogen or a proton. So a base does not need to be soluble in order to take a proton. So this is actually referred to as surface chemistry. So the acid-base reaction will occur on the surface of, whatever your reaction medium is. So you're actually reacting with external protons. So some examples would be sodium hydride, potassium hydride, and lithium hydride. So for example, these all pretty much work the same, but if we look at lithium hydride, lithium is positively charged, which means that hydrogen is negatively charged. And a negatively charged hydrogen is really unstable. So it definitely wants to react with positive hydrogens or protons to form hydrogen gas. So again, H minus is very reactive. However, you can have side reactions with moisture in the air. So that is problematic because you really don't want to have side reactions. Additionally, the product H2 is flammable. So that's another problem with using this type of base. So there are some very specific reactions where hydrides are useful. But probably most of the time we'll end up using either a bulky base like tert butoxide to favor elimination or a special base like DBN or DBU. All right, now what if we want the opposite? What if we want nucleophiles that are not bases? So one option is to use a halide. So the chloride ion, the bromide ion, or the iodide ion. So halides have a negative charge, which is good. That means they're very reactive, which we want for a nucleophile. But they're bad bases because they have strong conjugate acids, or the other way to say it is that they are the conjugate bases of a strong acid. Which means that they are weak bases. So that's perfect. That means that they're not really going to take hydrogens, but they are going to attack a carbon. Another option is to use sulfur-containing compounds. So, for instance, SH minus, or maybe the sulfur is attached to some sort of alkyl group. So remember R equals an alkyl group like methyl or ethyl, etc. Or you could use the neutral form where the sulfur also is bonded to a hydrogen. Now, R should not be bulky, so we'll just add a little asterisk. R should not be bulky. Because remember, the bulkier the nucleophile, the worse the nucleophile. And it's probably going to act as a base instead of a nucleophile if it's bulky. Okay, so let's summarize everything we just went over. And this summary would be a really good set of flashcards. Because as we go forward, we're going to try to pick bases or nucleophiles that will favor E2, E1, SN2, or SN1. So these are good to have in your back pocket. So let's just start with good base that's a weak nucleophile. So for a good base that's a weak nucleophile, we've said that we can use DBN or DBU or potassium tert butoxide. We could also use hydrides like sodium hydride, lithium hydride, or potassium hydride. All right, and then what about good bases that are also good nucleophiles? Well, we could use something simple like the hydroxide ion. So in this case, you might get a mixture of products. You might get elimination and substitution. Let's see, attached to any alkyl group really, where the alkyl group is non-bulky. Or really any strong base. Okay, now what if we have a good nucleophile that's a weak base? Or what if we need a good nucleophile that's a weak base? So we want to favor substitution reactions. So then we would need a halide. Or sulfur-containing compounds. And remember, R is not bulky. And then finally, what if we want to favor SN1 and E1? So we would need a weak base that's also a weak nucleophile. So options for that would be something like H2O, so water, or methanol, really any alcohol. So we could have ethanol, so those would be weak bases that are also weak nucleophiles. Okay, so now we have a lot of different tools in our tool belt that we can use to favor a particular type of reaction. So whether that is elimination or substitution, or we could go deeper and try to really get just the SN1 product or just the SN2 product. So I think we'll stop here. And again, I recommend making some flashcards for these different categories just so you can remember which is which. And you can also relate this back to the summary chart that we saw on the first page. So if we go back, remember that strong bases and weak nucleophiles favor E2. Strong bases that are strong nucleophiles, you'll get a mixture typically, unless you have a tertiary carbon. Weak bases that are strong nucleophiles will favor substitution reactions, and then weak bases that are weak nucleophiles will favor SN1 and E1. So you could also correlate the categories we just went over with this summary table too. Okay, so I hope that helps a little bit with kind of understanding the differences between elimination and substitution, as well as nucleophiles and bases. Let's see, I think next time we're going to go over elimination reactions in a little more detail. We'll talk about the mechanism a little bit more and what types of products we expect. So I will see you then.